In the last 4 decades, CPU speeds have exploded, but memory latency hasn't kept pace. We call this the memory wall. To bridge this gap, modern CPUs rely heavily on hierarchical caches, L1, L2, and L3. These caches are incredibly fast, but they only work if the CPU can predict what data you need next. When your code follows standard object-oriented patterns, it often creates a fragmented memory layout that makes prediction impossible. This leads to cache misses, where the CPU sits idle for hundreds of cycles waiting for data to arrive from RAM. In this video, we'll explore why the classic object is often the enemy of high-performance computing, and how we can rethink our data structures to work with the hardware, not against it.
The CPU doesn't fetch individual bytes from memory. Instead, it fetches data in fixed-size chunks called cache lines, typically 64 bytes. When you access one integer, the CPU brings in the next 15 integers along with it, assuming you'll probably need them soon. This is called spatial locality. If your data is packed tightly in an array, the CPU is extremely happy. It can prefetch the next lines before you even ask for them. However, object-oriented programming tends to wrap data in classes and instances. In many languages, these instances are allocated individually on the heap. This means that two objects that are logically next to each other in your list might be thousands of bytes apart in physical RAM.
This brings us to the core problem: pointer chasing. In a typical OOP language like Java, Python, or even C++ with classes, a list of objects is actually a list of pointers to memory addresses elsewhere. To process a single person object, the CPU first fetches the pointer from the array, then has to jump to a completely different memory location to find the actual data. This jump is a gamble. Because the destination is random, there's a high probability it's not in the cache. This is a cache miss. If you're iterating over 10,000 objects and every single one requires a random jump, your CPU is spending 95% of its time doing absolutely nothing but waiting for the memory controller. Even if you get the objects together, OOP adds overhead to the layout itself. Every object instance usually carries a header, which stores metadata like the type ID, lock state, or a pointer to a vtable for polymorphism. If you have a class with just 2 floats, x and y, the object might actually take up 24 or 32 bytes because of this header. This bloat means fewer useful data points fit into a single 64-byte cache line. You're effectively paying a tax on every byte of memory bandwidth. In a high-performance system, we want our data to be dense. We want as many relevant values as possible to arrive in every single cache fetch. The alternative is data-oriented design. Instead of thinking about things, like a player or a monster, we think about data. If we need to update the positions of 1,000 entities, we don't need their names, their inventory, or their AI state. We only need their x, y, and velocity values. In data-oriented design, we store these values in contiguous arrays. This is often called a struct of arrays approach. By stripping away the object wrappers and headers, we create a layout where every byte the CPU fetches is exactly what it needs for the current operation. This can lead to performance improvements of 10 times or even 100 times in compute-heavy loops.
Let's look at the numbers. In a standard benchmark, iterating over 1 million objects and updating a field might take 10 milliseconds using standard OOP pointers. The exact same logic using a contiguous array of primitives might take only 0.5 milliseconds. Why? Because the CPU is never waiting. It's constantly fed with data. Furthermore, because the access pattern is predictable, the hardware prefetcher can look ahead and bring the next cache lines from RAM before the CPU even requests them. This effectively hides the memory latency. Modern engines like Unity with their ECS system, or the Bevy engine in Rust, are built entirely around this principle to maximize throughput.
No. For high-level business logic, UI, or systems where you only have a few dozen instances, the convenience of objects is worth the cost. But when you are building a physics engine, a particle system, or a high-frequency trading platform, anywhere you process thousands of similar items, you must think about the cache. Remember, your CPU is a Ferrari, but memory is a traffic jam. Don't build your data structures in a way that forces the Ferrari to stop at every single intersection. Optimize for the hardware you have, not the abstractions you were taught. Thanks for watching.